they have rediscovered
It's not
the
that
void.
ancient. My grandfather helped build that building.
Ah, wow. Wow.
Okay, let me know what happens to the marble floors. He was in charge of laying the marbles.
Okay. When they're done, I'll let you know.
Okay, thank you.
Okay, everybody. So it's time. So if everybody's ready, maybe we can get started. So thank you so much for coming. It's really nice to see everybody from all over the world. So today we have Pavlos Motakis, and he will speak on coarse universality. Pavlos is from Illinois, Urbana. He's a postdoc there. I think everybody knows him. And he's in job market next year. So if you have a job, please reach out to him. Okay. Okay, Pavlos, take it away, please.
Thank you very much for the introduction. Thank you very much for the advertisement as well. So I'm also very happy to be given the opportunity to give a talk about the topic that I'm interested in this seminar, and I hope that it catches on and you have many people lined up who are willing to give a lecture here. It's definitely not a very difficult thing to do. I would just like to say it's very easy. I mean, as long as you just have something to write on or some slides ready, it's just something you can do very easily. Okay, so let me share my screen.
Okay, so before we start, everybody please look at your microphone if it's on, muted. Okay. And only when you have a question, you can unmute and ask questions. Thank you. Go ahead.
Right. So this is based on joint work with Florent, Gilles, and Thomas, who are all attending the seminar at the same time. So if I say anything wrong, feel free to jump in and correct me or provide supplemental information. So it is about coarse universality, and it's broken up into three sections. The first one is about Bourgain's overspill argument. The second one is about coarse embedding, and the third one is about coarse universality. So Bourgain's overspill argument is a descriptive set theoretic sort of direction or type of proof in Banach spaces that I find most people are very well versed with, because it is a very fundamental type of way of finding things inside Banach spaces. So especially older generations in the field know this topic inside out, I would dare say. But there are some people who don't know this topic so well, or they haven't stumbled across it. So I would like to take this opportunity and explain a little bit how it works without getting into, of course, the details of the proof. So secondly, I'm going to talk a little bit about coarse embedding. So this is a type of embedding that comes, if I'm not mistaken, mostly from group theory. They initially used it to study groups based on the coarse geometry of Cayley graphs. And I would like to make the connection to Banach spaces and how it has been used inside the theory. And finally, I would like to combine the two previous topics and how we can talk about universality in a coarse setting and how it relates to Banach spaces. Okay, so we start with Bourgain's overspill argument. I already tried to explain a little bit what it is. So what it is actually is you fix a Banach space and you try to find inside it a certain structure to witness a certain property it has by not observing the property directly. Instead, what you are trying to do is to sort of stratify the property, break it up into some components which are not individually sufficient to witness the property, but if you witness all of these individuals together, then the property all of a sudden must appear. So this is also why it's called an overspill argument. If you find all these things, none of which witness the whole thing, in the end of the day, they accumulate and the property must exist. Okay, so what are universal Banach spaces? So very, very generally, if you fix a Banach space X and a class of Banach spaces C, if every member of C is isomorphic to a subspace of X, and when I say here isomorphic, I mean linearly isomorphic as a subspace, then X is called universal for the class C. So some examples of class of Banach spaces that we study is the class of all separable Banach spaces, which we call SEP, the class of Banach spaces with separable dual, and of course by the Hahn-Banach theorem, these are all separable, and we denote them by ST, and the class of reflexive and separable Banach spaces. So in order to apply Bourgain's theory, we have to talk only about separable Banach spaces. The tools kind of seem to not work well if you leave the setting of separability. So the very first example of a Banach space within the context of our questions is due to Banach-Mazur, the theorem that says that the space of continuous functions on the unit interval is universal for all separable Banach spaces. And of course, it is itself a separable Banach space by the Weierstrass approximation theorem, for example. So therefore, it is a Banach space that is separable and is universal for all separable spaces. And before I proceed, there are some honorable mentions in this topic of universal spaces. There exist types of spaces that are universal for more structures rather than just for embeddings. For example, there are Pelczynski's universal spaces, and they are universal for bases. There is Gurari space, and there is also in other classes. You can talk about universality, for example. There is Urizon's metric space that is universal for space for all separable metric spaces. And in general, universality appears in this context in all areas of mathematics. So we are more going to look at questions in the direction of the theorem of Banach and Mazur. For example, we fix another class. Don't take all the separable Banach spaces. Take SD, which is the class of Banach spaces with separable dual. Can I find a Banach space that has a separable dual and contains inside it all Banach spaces with separable dual? Or switch to another class. Take the class of all separable and reflexive Banach spaces. Can I find one of those, a separable reflexive space, that contains all the others? And it turns out the answers to both of these questions is actually no. And the first and the earlier one is due to Schlenk, who proved that if a Banach space contains inside it, a separable Banach space contains inside it all other Banach spaces with separable dual, then this space actually cannot have a separable dual. Therefore, such a universal space does not exist. And the result of Bourgain, I will talk about it in more detail later. But his result implies that there is no reflexive space that contains inside it all reflexive Banach spaces. And let me just say that we are actually going to focus on the result of Bourgain. And the reason is that although Schlenk's result comes earlier and they are conceptually, they have some similarities, nonetheless, the proof of Schlenk does indeed prove that a space that contains inside it all spaces with separable dual does not have separable dual. So it gives some information about such an X. However, this information is not very concrete. It's a little bit qualitative and it's not very specific. On the other hand, Bourgain's method, it can give a lot of information on what one can find inside a space if it contains inside it all reflexive Banach spaces or also other examples of classes. And one could also say that, in fact, Bourgain's result is more influential, and this approach has been used many, many times since. Also Schlenk's approach, but Bourgain's approach has probably had more applications. Although I don't want to say that Schlenk's result is important. Certainly Bourgain came after him and he was probably inspired by him, and many results have used Schlenk's technique as well, many. Okay, so now, as I said, I want to take the opportunity and talk a little bit about Bourgain's result. And to talk about Bourgain's approach and result, we have to agree on some notation. So we fix a set A, and by A to the strictly smaller than omega, we will mean all finite sequences of elements of A. And let me say here, this also includes the empty sequence. So this is a convention that makes sense from a topological point of view. So we will also include the empty sequence. And my handwriting might be a little bit substandard, and it's not always the best, but one thing that doesn't help is that I'm writing on a vertical surface at this point, on a vertical glass surface. But I hope you can read it. If you can't, let me know and I'll try to repeat or rewrite. Okay, so what is a tree over a set A, a non-empty set A? So a tree is a collection of finite sequences of elements of A. So it's a subset of A to the smaller than omega, so that whenever I take a sequence, which is a member of T, I equals 1 to n, and I forget the last entry of the sequence, then this is still an element inside my tree. So this is sort of downward closed. Whenever I cut off the element the last element of a sequence in T, then this is still in T. And by this, we also deduce that it must contain the empty sequence. The empty sequence must be inside any tree. So let's look at an example or two. Take the set n, the natural numbers, and let me just write here for us in this lecture, the natural numbers start at 1. We'll just go this way. So the set of all strictly increasing sequences of natural numbers is a tree. It is not all sequences of natural numbers. It is a subset of it, and it is closed under taking such a sequence and cutting its last entry. So this would still be a strictly increasing sequence of natural numbers. And by convention, we also mean the empty sequence is a strictly increasing sequence of natural numbers. So a remark for any tree would be that it is a partially ordered set. If I take two sequences, AI, I equals 1 to m, and BI, I equals 1 to n, then we say that AI comes before BI in this partial order if it is shorter, AI is shorter than BI, and for the first m entries of BI, they coincide with the first m entries of AI. For example, if we go to the set of strictly increasing sequences, if we take the sequence which is 3, 7, 8, this strictly increasing sequence, and we extend it, so we take it and then put something else after it and maintain its strict increasingness, then this is the second sequence is one that comes after the previous one in this partial order. Okay. So a tree will be called well-founded if it contains no infinite, totally comparable subsets. What this means is that I cannot find an infinite collection of sequences, all of which extend each other. So let's look at an example of a well-founded tree over the natural numbers. So instead of all the strictly increasing sequences of natural numbers, consider all the strictly decreasing sequences of natural numbers. Now, because the natural numbers are a well-ordered set, a strictly decreasing sequence has to be finite. Therefore, if I were to find an infinite collection of strictly decreasing sequences, all of which extend each other, I would be able to find an infinite strictly decreasing sequence of natural numbers. So this cannot happen. Therefore, this tree here is well-founded. So, so we want to talk about how we start with such a tree, a well-founded tree, and how we can measure its complexity. So given a well-founded tree, we will define its derivation as follows. I take all of its maximal elements and I erase them from my tree. I completely forget them. And we will look at an example in a moment. And then I take this new set, which is T removing all of its maximal elements with respect to this partial order we defined earlier. And this is T derivative or T prime, and we actually also call it a pruning of T. So we just pruned it. We took all the maximal elements and we clipped them off. So a remark is that a well-founded tree that is not empty does have maximal elements. And this is something that one can show by a relatively easy argument, by chasing down the rabbit down the hole. If you assume that it doesn't have maximal elements, you can construct a sequence which has to be strictly increasing in the order, and this does mean that it would not be. So therefore, as long as our tree is not empty, then its derivative is a proper subset. I got rid of something. So by transfinite recursion, we can differentiate whatever we found consecutively as follows. So I start with T in my first step. So this I call the zeroth derivative, just as we do with functions. And then I can inductively define derivatives of all orders by differentiating whatever I differentiated until now. So the second derivative, the third derivative, and so on and so forth. But these are sets. And as sets, and in fact a decreasing sequence of sets, I can take their intersection. And then I call this T omega. And now I have a new tree. This is still a tree. This is not extremely difficult to see. And since I have a tree, I can differentiate it again. And I call this T omega. This one I will call it T omega plus 1. And then I can differentiate again and again and again. And for any natural number, I can define T to the omega plus n. By whatever set I take in every step, I can differentiate again. And now I have a sequence here. For every n, I have a T omega plus n. And I have a strictly decreasing sequence of trees. I can intersect them. And this I would call T omega times 2 because I did the omega step twice. And this goes on. And I can do this as many times as I need. And at some point, for some ordinal number, so these omegas and these steps that I repeat, they are indexed over ordinal numbers. So it's a process that has steps, and it has limit steps and successor steps. And at some point, because I have a sequence of sets which decrease, and whenever in any step the sequence of my set is not empty, the derivative would be a proper subset. I have a sequence of sets that strictly decreases until at some point I get rid of the whole thing. So for some step, some ordinal alpha, the alpha derivative is going to be empty. And the first alpha for which this happens, we will call this the order of our tree. So let's look at a specific example. Take a set of all strictly decreasing sequences of natural numbers. Now, we want to look at the derivatives of this set, and we want to understand what the order of this tree is. So what are the maximal elements of all finite strictly decreasing sequences of natural numbers? It is all sequences of natural numbers that decrease strictly and I cannot extend. When can I not extend a strictly decreasing sequence? When its largest entry is the smallest possible. Whenever I cannot concatenate by any natural number so that it remains strictly decreasing. So this means the final entry must be the smallest possible natural number, which is 1. So the maximal elements are all strictly decreasing sequences of natural numbers whose final entry is 1. So if we get rid of all of these elements, so we take the first derivative, then the sequences that remain are those whose final entry has to be at least 2. I got rid of all of those where the final entry is 1. Okay. And by extension, when I do this for any step, if I take the nth derivative, I remain with all strictly decreasing sequences whose final entry has to be at least n. And of course, in every step, we still have the empty sequence, as I have written here, and I forgot to mention. And I repeat this for every natural number. And then at the omega step, I take the intersection of all the tn's. And now I got rid of all of the strictly decreasing sequences, because every strictly decreasing sequence, its final entry is something, it's some natural number n. So in the n+1 step, I got rid of it. And all I was left with is the empty sequence, because the empty sequence existed in all of these steps, in T1, T2, Tn, and so on and so forth. So when I differentiate one more time, I got rid of that. It was the only element, it was a maximal element, so I was left with the empty set. And therefore, the order of this tree here, all strictly decreasing sequences of natural numbers, is omega plus 1. Okay, so now I hope we understand a little bit what trees are, what deriving trees means, and how we can understand the complexity of a tree, the index of a tree, by differentiating, clipping it or pruning it until there is nothing left. And we looked at a couple of specific examples. So now here is what Bourgain did. So he fixed a Banach space X, let's call it X0, that has a normalized basis. For example, you can fix X to be the space of continuous functions with a unit interval, and EI could be the Schadler system, which is the basis for that space. Now, for a Banach space Y, so our X0 and EI is fixed. Now look at a Banach space Y, and look at a constant C, a positive constant. Actually, it would also have to be bigger than 1, but it doesn't matter. Now, for this X0, EI, Y, and C, we will define a tree. This tree is going to be a tree over Y, so it will consist of sequences of elements of Y. And it is not all of them. It happens to be all sequences inside Y, finite sequences, that are C equivalent for this fixed C to the first K elements of my fixed basis EI. So I have inside Y all these finite sequences who witness up to this constant C an equivalence of the first elements of the basis EI for the length of the pieces YI that I considered. So let's try to look at one example, not very explicit, but if we take EI to be an orthonormal basis of a Hilbert space, and we take C to be any constant strictly bigger than Y, and we fix any infinite dimensional space, then by Dvoretsky's theorem, I can find all finite dimensional Hilbert spaces almost isometrically represented, so as close to one as I wish, in particular C close, inside Y. So for every n, or for every k as I wrote here, I can find a sequence yi equals 1 to k inside Y that as C equivalent to orthonormal basis of length k. So from this, I can deduce that this tree here, for every infinite dimensional Banach space, if EI is an orthonormal basis, has to have branches of every length. And therefore, when I start pruning the tree, I will have to use at least countably as many steps as the natural numbers, which we call omega, to get rid of all of them. Therefore, this tree here is a tree that has order omega. So this is something that we can find in every infinite dimensional Banach space. Of course, depending on what our Banach space Y is, we will get such a tree that is of different complexity. It can have different sizes. An observation is that if our Banach space Y contains an isomorphic copy of a Hilbert space, then inside this Banach space Y, I will be able to find an infinite sequence Yi, which is equivalent to an orthonormal basis. So therefore, inside this tree, I would be able to find an infinite branch. So this tree would be ill-founded. So if Y contains an isomorphic copy of my Hilbert space for this particular example, then this tree here for the orthonormal basis of a Hilbert space would be ill-founded. On the other hand, if we assume that such a tree is ill-founded, then this means that there exists such an infinite collection of sequences, all of which extend each other. And if they all extend each other, they define an infinite sequence. And this infinite sequence would be then C equivalent to the whole sequence EI. And therefore, I would find the sequence EI, a sequence YI equivalent to the whole EI inside Y. Therefore, I would find an isomorphic copy of my Hilbert space, in this example, the Hilbert space, and it would embed it inside Y. And of course, this works for any Banach space X0 with the basis. It doesn't have to do with the fact that there's a Hilbert space. So whether my space X0 embeds isomorphically into Y is exactly the same as saying that for this tree here, for some C, depending on how good the embedding is, I can find an infinite branch. So if an infinite branch exists, then we say this tree is not well-founded, namely it is ill-founded. So whether X0 embeds into Y depends on whether this tree is well-founded or ill-founded. So here's what Bourgain proved. If you fix a separable Banach space and you have fixed an X0 and an EI as before, then if the complexity of all of these trees for all positive C's is omega 1, so it is not a countable ordinal number, but it is the first uncountable ordinal number, then X0 has to embed into Y. So in fact, what it says is, I don't have to find the infinite sequence YI inside Y that witnesses the equivalence with EI. Instead, I just need to show that there exist trees of such sequences of unboundedly high complexity. And the corollaries, two corollaries that we can deduce from this theorem is the following one. If a separable Banach space contains all C of K spaces for K countable and compact metric spaces, then Y must contain inside it all separable Banach spaces. And the second corollary, the one that we mentioned earlier, is that if Y is a separable Banach space and it contains inside it all reflexive and separable Banach spaces, then it has to be universal for all separable Banach spaces. And the reason for this is because, let's say for every alpha, which is smaller than omega 1, there exists a reflexive and separable, let's call it X alpha, such that this index from above which I could, as an index, I could use any sequence that I want. I could use, for example, C01 with the Schauder system. Let's say Sn. So that this is as high as I wish, at least alpha. So this means if a Banach space contains inside it all separable and reflexive Banach spaces, then because all of these have unbounded such index here, then this space would have to have unbounded index. Therefore, C01 with the Schauder system would have to embed inside the space. So because the space C01 with the Schauder system is universal, Y would have to be universal. And let me just say that this is actually specifically the type of result that we will try to translate in a course setting. So what is going on here is that you have a property, for example, being universal for all separable Banach spaces, which is the same as containing C01, and you have all these pieces. All the pieces that I am referring to are all separable and reflexive spaces. The existence of a separable and reflexive space on its own inside the Banach space is nowhere near being able to witness the fact that this space is universal for all separable Banach spaces. But when you have them all collectively inside the space, then this has to happen. Then you have to be universal for all separable Banach space. So this is what I mentioned at the beginning. You have this property containing C01. You don't have to witness it at once, but you can just witness these pieces of it, which are individually unable to testify to the final property, but all of them together, they can speak in one voice and say that yes, the space is universal. And just one comment in the proof of Bourgain's theorem. So I'm not going to say what the proof is, but once you have the tools, when you have decided what you want to define, then the proof is not so difficult to follow anymore. I mean, it uses some topological arguments, but in the end of the day, it comes down to the fact that if you take a complete separable metric space, then you cannot find an uncountable chain of open sets which are disjoint from one another. And basically that is what it boils down to. So it's just a cardinality argument and separability. Okay, so we talked, I hope I gave some flavor of how Bourgain's technique works, how you can witness a certain property, such as being universal for all separable spaces, just by looking at certain pieces of it individually and finding all of them in unbounded complexity. So now I want to switch a little bit the topic to talk about coarse embeddings briefly, and then I want to tie them together. So coarse embeddings, they are a very weak type of embedding, and they are defined between metric spaces. So I have two metric spaces, x and y, and I have a function f from x to y, and I call this a coarse embedding if the following thing happens. There exist two functions, rho and omega, and their domain is the positive side of the real line, and they also take positive values, so non-negative values, with the following properties. If I push rho to infinity, then it blows up, it goes to infinity, and for all xy in x, if I look at the distance of their images, then this value is going to be bounded below by rho of this distance of the points and bounded above by the omega of the distance of these points. So I have these two functions, rho and omega, that control the distance of the image of 2 points, and the control is based just on the distance of the points. It is not based on the points on themselves, but just the distance of the points. And there is actually no assumption on what these rho and omega are. They don't have to be linear. They don't have to satisfy any condition. One could add a restriction that they are increasing or that rho is smaller than omega, but it is not entirely necessary. So here's a picture that tells us what's going on. So what does it mean that this f is a coarse embedding? So I fix a point x. I take a ball around x of radius lambda, and then I go at f of x and I take the ball around it of radius omega of lambda. So omega is this function that is given. Then anything that has distance at most lambda from x, its image will have to fall inside this ball of radius omega of lambda. So as long as the distance is at most lambda, the distance from f of x, the image has to be omega of lambda. So it doesn't depend on x. It just depends on the distance from x, which is at most lambda. And on the other hand, if I again look at the left, at this ball of radius lambda, I go at the right and I draw around f of x this ball of radius rho of lambda, which is a number smaller than omega of lambda. Then if I take something that is lambda away from x, its image must be rho of lambda away of f of x. So this blue area on the left maps to this blue area on the right. And of course, because rho of lambda is assumed to go to infinity, if I start increasing this radius here, then this radius here must also be increasing. So as I clear up around x and I push the blue area away, in the image, the blue area must also be pushed away. So this is what it means that rho of t goes to infinity. So if such an f exists, then we say that x embeds coarsely into y, or we write this symbol here to be more brief, x hook arrow course into y. So one more comment, I will not refer to this during the lecture, but this is actually hidden inside the proofs. If you have a collection of metric spaces xi, indexed over some set I, and they all embed coarsely into y with such rho omega which don't depend on I, so they are the same rho on omega for all i's, then we say that this collection of metric spaces embeds equicoarsely into y. So to understand a little bit what coarse embeddings are, let me give a few examples. Coarse embeddings, as I said, it's a very weak notion of embeddings. For example, the real line embeds coarsely into Z, and the coarse embedding would be you take every number and you send it to its integer value, and this is indeed a coarse embedding. So the intuition that we get from this is a coarse embedding has the following property. If I look at R and Z from far enough apart, they look the same. So if I twitch my eyes a little bit and blur the image, then the points in Z start looking more or less like a line. So from far away, they look the same. Another thing that one might observe is that any bounded metric space embeds coarsely into a point. And the reason is because if I look at a bounded metric space from very far away, indeed, it looks like a point. So this confirms our intuition of things looking the same when we look at them from far away. The most surprising example, actually, is that, this is not the only thing that the only way in which one can interpret a coarse embedding. Take inside the real line all powers of 2, and with the usual distance in R, look at this metric space. It's all positive powers of 2, and then look at all squares of natural numbers. Then, if I take the map that sends 2 to the n to n squared, or vice versa, the map that sends n squared to 2 to the n, these are coarse embeddings actually. And this is an exercise to find the rho and the omega. You can actually find them explicitly what they are. I don't remember now what they are, but you can find them explicitly. And this is quite surprising because in the metric space X, the distance of 2 points is a lot bigger, and the rate at which it changes is a lot faster than as if you look at the metric space Y. And another intuition that we could give at this is what we look at X and we look at Y at this distorting lens. And after looking at this distorting lens, they still look the same. So a coarse embedding is not only 2 things look the same if we blur them out, but we can also distort them with a lens, and then if they still look the same, they would still be coarsely equivalent. So in the setting of Banach spaces, so saying that coarse embeddings are weak, we can find many Banach spaces embed coarsely into one another, even though they're not isomorphic as Banach spaces. For example, for P between 1 and 2, every capital LP embeds coarsely into a Hilbert space, which is not true for linear sense. And a Hilbert space embeds coarsely into all little LP spaces. So although coarse embeddings are weak, they are not entirely useless. They do carry some weight. You can't say that everything embeds coarsely into anything. There are restrictions. So one example would be, so it's not the earliest one, but it's very Banach spaces. So it says that C0 does not embed coarsely into any reflexive Banach space. So the structural property of being reflexive prohibits C0 to embed coarsely into a space with this property. So it is impossible. Some other examples include if you go for a P bigger than 2, then you can no longer embed those little LP spaces into a Hilbert space, which for P smaller than 2 you can do because of this theorem here. But if you go bigger than 2, then you can't anymore. Okay, So we are still within the conversation of coarse embeddings and how weak they are. So this is a natural question which has lingered around for about a decade before it was answered. So coarse embeddings are weak. They're not entirely weak, but we saw, for example, that Hilbert space embeds into all LP spaces. Can I say that the Hilbert space, the separable infinite-dimensional Hilbert space, embeds coarsely into every infinite-dimensional Banach space? I mean, there are two justifications as to why this might be the case. First of all, link L2 embeds coarsely into all Hilbert spaces. And secondly, there exists Dvoretsky's theorem, which I thought I had typed, but I didn't. Dvoretsky's theorem says that the Hilbert space is finitely representable in every infinite-dimensional Banach space. So in this sense, I can find it inside every infinite-dimensional Banach space. And finite representability is a weak sense. So in this weak metric sense, maybe can I say the same thing? Is the Hilbert space coarsely represented in every infinite-dimensional Banach space? And this is a very natural question after the preceding results, but the answer turned out to be no. And this is a relatively recent result due to Florent, Gilles, and Thomas, who proved that the Hilbert space does not embed coarsely into T star. And T star is actually the original Tillotson space, or the dual of what is called nowadays Tillotson space. And it is quite interesting that this specific example, almost 50 years after it was defined, it can still be used directly without any modification to answer this type of very natural questions in metric geometry. So let me say something now that this space T star, the original Tillotson space, has a property which is called reflexive and asymptotic to zero. So this is a property that I want to define in a moment. But before I define it, let me just say that the reason I have boxed it and put so bright colors around it is because this is a central property during this lecture. I will talk about it more later if I have enough time, because apparently time is going too fast. So T star is the space that has this property. It's reflexive and asymptotic C0. And note that this is a property that has C0 inside its name. And your intuition would be that little L2 should satisfy no property that has anything like C0 inside its name. And your intuition would be correct. L2 is not an asymptotic C0 space, although it is reflexive. And so it is maybe appropriate at this time to say that a little bit after the above was proved, we were able to slightly improve this theorem by showing that if you have two Banach spaces and X is reflexive and asymptotic C0, it has this property, which I will define in a moment, and Y embeds coarsely into X, then Y also has to be reflexive and asymptotic C0. So although these coarse embeddings are very weak, some properties are preserved to them, and reflexive and asymptotic C0 is a property that is preserved under coarse embedding. So this would mean that the class of reflexive asymptotic C0 spaces is coarsely rigid, or it is closed downwards under coarse embeddings. And this is a little bit interesting because there aren't that many classes that are well known to have this property, there are not many properties that are known to be rigid under coarse embeddings. Such properties would be, for example, being finite dimensional, and a few more which are not too easy to define. Right. So what I want to do next is tell you what a reflexive asymptotic C0 Banach space is. So to do that, we have to go back to trees. So there are many ways to define it, but since we talked about trees, I will use the way that I go through trees. So we fix a natural number k, and we call tk the tree over natural numbers that consists of all strictly increasing sequences that have length at most k. So this is a fairly simple tree. So we fix a Banach space X, and now we want to define a normalized tree of height k inside the Banach space. This is going to be a collection of norm 1 vectors indexed over this tree here of strictly increasing sequences of length at most k. And I have a picture here. If we take, for example, k equals 2, and we have all strictly increasing sequences of length equals 2, they look like so. I first have the empty sequence. Then I have sequences of length 1. Here they are, all of them, and dot, 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 they go on. There are infinitely many. And after, for example, the sequence that has only 1 as an entry, I can look at all sequences of length 2 that start with 1. and they also continue. There are infinitely many. And then I can look at all sequences of length 2 that start at 2, and so on and so forth. And this is an infinite tree, and it is called it's called T2. And the normalized tree of height 2 is just a collection of vectors indexed over the nodes of this tree. So a way to think of such a tree of vectors, a nice way to think of it, is to look at all of these maximal branches. And now each of these maximal branches in the tree defines a sequence. In fact, it's a sequence of length 3 because you also have the empty sequence. And the tree can be thought of as a collection of all of these sequences that are interwoven with one another in this way. So it's a collection of finite sequences that sort of cohabit together, and they are entangled in a certain way or interwoven. So now I want to talk about a specific type of such a tree. So such a tree will be called weakly null, or a normalized weakly null tree of height k, if I fix any S, any sequence, strictly increasing sequence, which doesn't have length k, but it has strictly smaller length. For example, I look at this sequence here, it goes up to 1. And then I look at all possible sequences that extend it, all of these terms here. They form a sequence that converges to 0 in the weak topology. So they form a weakly null sequence. And this happens for every bunch of nodes here that hang directly under a common node. If they all converge weakly to 0, then we call this a weakly null tree. And the meaning behind this is the following. If a sequence, a norm 1 sequence, goes weakly to 0, what this actually means is that this is not very precise, but what it more or less means is that it evades all finite dimensional subspaces of your space. So these sequences eventually go deeper and deeper inside your space. Right. So this is a tool that we need to talk about asymptotic C0 Banach spaces. So a Banach space will be called asymptotic C0 if it does not contain an isomorphic copy of little 1, and there exists a uniform constant C, so that for any k that you give me, and for any normalized weakly null tree of height k, like this inside the space, I can find one branch, so one such maximal thing from the root that goes all the way down to k, so that if I look at this sequence here, defined by these terms, it is going to be C equivalent to the unit vector basis of L infinity of its length. And this is, if this happens for all such trees, then there is some Ramsey argument that says that actually in this tree I will find many such branches. If there exists one, there have to be many. And this is not entirely evident from this definition, which is actually not the original definition, but it comes well together with what we talked about so far. So if you find, if you have this definition, it is not evident, but this more or less means that if you fix a number k, then there's a very precise sense in which if you pick k vectors that live far enough from apart from each other, then they have to define a sequence that is C equivalent to the unit vector basis of L infinity of k. So this is more or less what this means. Right. So now, in the time that I have left, I can talk as much as I am allowed to about coarse universality. So we talked about coarse, we talked about universality in a linear sense, the sense and the tools that Bourgain used to study it, and we talked about coarse embeddings. Now we want to combine them together, and let's see how much we have time to say. So a metric space will be called coarsely universal for a certain class of metric spaces if every member of the class embeds coarsely in the space. Some examples of classes, we could again look at all separable Banach spaces because Banach spaces have a metric, so they are metric spaces. Or we could look at the class of all separable metric spaces. So it's slightly bigger than the class of all separable Banach spaces. So a theorem due to Aaroni is that if we take C0 as a metric space, then every separable metric space embeds into C0 in a Lipschitz sense. Now, something that we can deduce by this, because Lipschitz embeddings are coarse embeddings, C0 is a separable metric space, and it contains inside it coarsely all separable metric spaces. Because it contains all of them Lipschitzly, it must also contain all of them coarsely. And in particular, what we can also deduce using this is that if we have a metric space, let's say a separable metric space, and C0 embeds coarsely into M, then M is universal. for all separable metric spaces. Because C0 is coarsely universal and everything embeds coarse into C0, therefore everything embeds coarsely into M, because coarse embeddings, their compositions are still coarse embeddings. The relation of being a coarsely embedded is transitive. Right, so here's what we proved, or what we observed. If you take a separable metric space and it happens to contain inside it all reflexive and asymptotic C0 Banach spaces, in a coarse sense, then it must contain coarsely all separable metric spaces. So there is this class of reflexive asymptotic C0 spaces. And let me say, separately, each of those reflexive asymptotic C0 spaces, they are not coarsely universal. Okay, reflexive asymptotic C0 spaces, remember, it's a class that is closed under coarse embeddings. If you find any other Banach space inside the reflexive asymptotic C0 space, it has to be reflexive asymptotic C0 space. So none of these spaces is coarsely universal. But if you witness their existence, all of them together inside the separable metric space, then this forces the space to contain inside it all separable metric spaces. And a comment on the proof, we have two proofs actually, and we wrote them both. The first proof is based on a theorem of the thus, and this proof is very short. It's like a half-page proof, but it's very opaque. So unless you understand the tools used in that proof very, very well, the proof doesn't say very much to you. And this theorem of the thus, it's on this theory of amalgamation of Banach spaces, and other people that have worked on it are, for example, Arios and Ferenczi. And there are several results in this direction, but we used explicitly this one of the thus. So I don't want to talk about this proof. The proof that I would like to have talked about, and let's see how much time you can give me, is another proof that imitates Bourgain's overspill argument in a nonlinear setting. And I will say, at least from my point of view, this is an intuitive proof. So as long as you understand Bourgain's overspill argument, this is an intuitive proof. It goes along the same lines. But unfortunately, we have made some extra set theoretic assumptions to prove theorem 5. In fact, we use the negation of the continuum hypothesis plus Martin's axiom, and we use a very specific corollary of it. And if I have time to get there, I will tell you. A small note to make is that if we remove the set theoretic assumptions, then we prove something almost as good as theorem 5. I'm not sure why it says theorem 5 here. I think this is a relic. I took this from another lecture and I forgot to remove 5. There is no 5. So let me X this out. So if we remove the set theoretic assumptions, then we can prove something almost as good. Then we can forget M here. And if we change it to M to the 4th power, we can remarkably prove without set theoretic assumptions that all separable metric spaces would embed into M4th, but not into M. So this is why I believe that actually one can use Bourgain's overspill argument to prove this theorem here. Without using the extra set theoretic assumptions, because we can prove the theorem with M to the 4 without set theoretic assumptions. But for some reason, to go to M, we have to use this assumption. So Bunyamin, how much time are you going to give me? Well, I will continue and you can stop me. Okay, so let's talk about Bourgain's way and see how we can change it into a linear way, in a non-linear way. So what Bourgain did is you fix the Banach space Y, you fix the constant C, and then you, for a given sequence, a Schauder basic sequence, you want to represent it inside Y. And how did you do it? You look at all these finite sequences which witness the equivalence to an initial segment of this infinite sequence EI. And the observation is that the statement that this yi is equivalent to ei, even though it is for this finite dimensional space, this is an inherently linear statement, because witnessing whether yi and ei are equivalent, you have to check all linear combinations of them. You can't just check those k elements of the sequence. So this is inherently a linear statement. So what can we do to make this into a non-linear statement? let's see. So now I will tell you more or less what our approach of the nonlinear Bourgain index is. There are different approaches. Maybe ones are simpler. I find this one to be sort of natural, and this is the one that we kind of needed to work in the asymptotic C0 setting. So we look at this skeleton inside C0 of all functions from n to z So here is also a relic. This is a mistake. For this is finite, whose support is finite. I look at all finitely supported functions from n to z, and I call this C00 of z. Now, this is a space of functions, okay? And they are functions with finite support, so they are bounded functions. Therefore, I can look at the uniform distance of two functions, and this is a metric space. And in fact, this lives naturally inside C00 of n, which is the space of all eventually zero sequences. So I just look at all eventually zero sequences with integer entries, and this is also another way to witness C00 of z. And I have forgotten to erase all these things. And this is just all there is. So a remark is that I can embed C0 coarsely inside this C00 of z. And don't look at this formula too much. Actually, what you do is you take any sequence EI, and which lives inside C0, and then you just look at the integer parts of its entries, and then you send this to C00 of z. And I wrote it a little bit funnily here because for negative numbers, the integer part is defined in the wrong way for us. So you just have to define it slightly differently. So this C00 of z in the core sense contains inside it 0, and it is enough to witness C0. Now, however, we want to use C00 of z in a very specific sense, and let's see what we're going to do. So now things start getting a little bit funny. So here's what we will do. For any finite set G inside the natural numbers, we will define this funny set, brackets ZG, to be all functions from n to z with support inside the G. So a natural way to think of this would be as z to the g, which is all functions from g to z. And it is fine if you imagine it as such. But for technical reasons, we want to imagine it as all functions defined on all of n, because we want them to just have zero values everywhere outside the g. So this is a collection of functions. A bunch over a set X is a collection of vectors xf indexed over some such zg, period. You take such a thing zg, and now if you fix a set, a bunch is a collection of vectors indexed over such a zg. That's what it is. So a remark is that if I have two bunches, chi and phi, this should have been psi, and it doesn't matter, chi and phi, let's call it chi and psi because this is psi.
Do you simply mean, Pavlos, do you simply mean all integer coefficient vectors who supported G? You can think of like in
yes, their support is inside G. It doesn't have to be all of G, it's inside G. So you can imagine.
So I mean, if you look at inside C0, you're just looking at all the integer valued vectors. Collection of all integer valued vectors with support is equal to G. Not
equal, inside G.
Inside G, okay. Yeah.
Yes, you can be 0 at some points in G.
Okay.
Yes. And this is it's important to take all of them. So, and a bunch is just like a collection of vectors inside a set, which is indexed over such a ZG. You index over it. Now, if I take two bunches, and a bunch is a generalization of a finite sequence in our sense. If I take two bunches, I can compare them. I can say that the bunch chi is smaller than the bunch psi if, so one is indexed over ZG, the other one is indexed over ZF, if G is actually F outside its maximum. So I clipped F by its maximum and I got G. And for every member of ZG this here, so every function with support inside G, I have assigned to it a vector XF, but also for every F with support inside G, this is also an F with support F, because G is a subset of F. Therefore, YF is defined, and I want this to be equal. So I can now define a vine. Given a set X, a vine is going to be a collection V of bunches so that for every bunch inside this collection, for everything that comes before this bunch in this partial order, then this is also in V. So the remark is that a bunch is going to be a tree. And this is not a tree in the sense that we defined earlier. It's actually a tree in a more general sense. It's a tree in the sense that this is a partially ordered space, where for every element, its predecessors are a finite, totally ordered set. And I guess I don't have much time to say any details.
But the bunches are not finite, so right?
They are not, but
bunches themselves are not finite.
You can finitize them if you want, but I'm trying to keep it as simple as possible.
Okay.
You can finitize them. It is possible. But you're right, they're not finite. So now, given on this notion of a bunch, you can go for a given metric space. You can look at the coarse C0 tree inside the metric space defined in this way. And now, instead of looking at finite sequences, you look at these bunches. And you look at all the bunches with the property that the distance of any two elements of the bunch is controlled by the distance of the functions over which the bunch is indexed. And then when I say the distance, I mean the uniform distance. And now this defines some sort of representation of C0 inside M. And of course, this representation I have also defined it so that it depends on some rho and some omega. So this is now a tree, and now for this tree, I can define its order the way we defined it earlier. And I can define the coarse index, the coarse C0 index of the metric space M to be the supremum of the indices of all of these trees over all rho and omega. So this is sort of just imitating Bourgain's definition. And instead of finite sequences, which Bourgain did, we look at these bunches. So the right way to think of it is that this C00 of G not of G, excuse me, of Z is analogous to N, and all these sequences here are indexed over finite intervals over N. And all these bunches are indexed over these ZGs. And these ZGs, the way we think of them, are as finite intervals, the analog of finite intervals in this index set. Now the theorem, okay, skip this. Let me just say the theorem, is that if you have a separable metric space, then assuming Martin's axiom and continuous hypothesis, if this coarse index is omega 1, then C0 embeds coarsely into M, and that's all separable metric spaces embed coarsely in M. And without any set theoretic hypothesis, if this coarse index is omega 1, then C0 embeds coarsely into M to the 4. And thus M4 is coarsely universal for all separable metric spaces. And let me remind you here that I stated before the first bullet as a theorem. So as we said, we can prove this using a theorem of Pavlos without, sorry, excuse me, that's not what I said. That's a mistake. We can't prove this with using a theorem of Pavlos. The theorem of Pavlos does not use a coarse index. So I have to take that back. But the corollary actually we used the theorem of Pavlos to prove. But the corollary using this here is that if you take a separable metric space and it contains coarsely all reflexive asymptotic C0 Banach spaces, then it contains coarsely all separable metric spaces. And the proof using the above statement, namely negation of continuum hypothesis plus Martin's axiom, is that for every countable ordinal alpha, there exists a reflexive and asymptotic C0 space, which is the Chilson space of order alpha, in particular its dual, which has coarse index at least alpha. And therefore, M must have an unbounded index. So therefore, by this theorem here, with set theoretic assumptions, you can embed C0 inside it. And I repeat, if we don't use the set theoretic assumptions, you can go to the M to the 4. And this is why I believe that this approach here should work without the assumptions. We just don't have the right proof. This is what I think. And that's all I had to say, and thank you. And I apologize for being many minutes.
No, that's good. Thank you so much for a great talk. I want to start with the most obvious question. So what's those assumptions are used for, the set theoretical assumptions in the proof?
Yeah, I mean, so the negation of continuum hypothesis plus Martin's axiom basically says that if you take an uncountable sequence, a transfinite sequence of infinite subsets of the natural numbers, infinite, such that for all alpha smaller than beta, M alpha is almost contained, almost, so up to, with the exception of finitely many terms. So this is for a transfinite sequence. Then there exists an infinite M such that, what way is it now? So that M is almost contained in all of them.
So you mean diagonal exist, right?
Yes.
Okay.
So you can diagonalize.
You can diagonalize for transfinite collections of sets that are almost contained in one another. So this is actually all we need.
Is it a silly thing might be possible that under this axioms, you know, maybe in the collection, maybe the nonlinear embedding already implies some sort of linear embedding? Like, did you think about that, or is it?
We're talking about coarse embedding, so unlikely.
Okay.
But you can modify all this coarseness into Lipschitzness. You can do this without too much trouble.
Pavlos,
Yeah.
maybe what you can mention also is that if we look at by Lipschitz embeddings, then you don't need the axioms, because then you can.
Yeah, no, this is, yeah, no, you don't. This is, but I focused on the course, you're right. If you go to Lipschitz, you don't need axioms.
Okay.
I have a slight correction to make.
Yes, please. Yes.
The result you attributed to Bourgain is actually Schlenk's result. That there's no universal reflexive space is actually Schlenk result. What Bourgain did is,
Right, I see.
if a space is universal for all reflexive, is universal for all separable spaces.
Okay, okay, thank
It's
you.
actually the title of Schlenk's, I looked it up, it's the title of Schlenk's paper. There are no...
You're right, but you're right, I remember now, that's exactly what he
Sorry,
proved.
there's Bourgain's thing was that he proves that it's universal for all and in some
Thank
sense,
you for the correction. You're right. So that's exactly what he proved. I remember Schlenk's proof now.
yes, he
Yes.
constructs, yeah, but okay.
The one that Bourgain proved was the C of K part.
Right, it's the universality that something which is universal for all separable, for reflexive is for all separable spaces, yeah.
Yeah. You're right. Thanks.
Okay. Any other questions?
Well, just maybe one comment, if you can hear me, about what was just said about Bourgain's work. Actually, one thing he did was observing that there was an extremely short proof using a null result of Yurevich on the fact that the collection of countable compact set is coanalytic number L. There was a very, very short proof, half a page, that if a space contains every CK with K countable, it's actually universal. Okay, this was a striking connection with descriptive set theory. I mean, that he did back in the 70s, actually.
Yeah, it was not I mean, his entire paper is based on descriptive set theory, at least the one that I was referring to. But I was not aware of this specific detail that you mentioned.
Well, if I'm not mistaken, this is in particular in his lecture notes, new classes of LP spaces. I mean, that was highly influential, of course, we all know that.
Yes. Yeah, I shall look that up, sounds interesting.
Okay, thank you. Any others?
So with this business of the Martin's axiom, or the cardinal T, or whatever it's called, is it because of the functions rho and omega that you can't use an ordinary sort of Kuhn-Martin boundedness?
So there are just too many. This is what's going on. So here's our problem. Our problem is that if you have coarse embeddings of a certain class of spaces inside the metric space, and our class is uncountable, then we cannot find inside a sufficiently large subclass where the embedding is equicoarse, where these rhos and omega are all the same. Using negation of continuum hypothesis and Martin's axiom, actually you can deduce this. And this is like the lemma. But in reality, if you want to go to M4th, you don't have to do this. And to show this M4, you have to do this very nice gluing argument, which Florent and Thomas are very familiar with, where you don't need equicourse. You do something much more elementary set theoretically, and then you do all the dirty work in some linearization argument. So maybe there is hope to get rid of this set theoretic axioms. But the reason is exactly what you said. It's the Rosen omegas.
Okay, thank you. Any others? Okay, if not, let's thank Pavlos. Thank you so much, Pavlos, for a great talk. And so